Welcome back to Append of Code 2021, day 23, almost at the end. It looks like tomorrow's is an easy one, like almost everyone did part 2, out of the ones who did part 1. Anyway, we're looking ahead, let's stick with 23. 23. A group of amphipods. So, amphipods. These are amphipoda. Malacostratsan. Crustaceans with no carapace and generally with laterally compressed bodies. Okay. Notice your fancy submarine and flag you down. With such an impressive shell, one amphipod says, surely you can help us with a question that has stumped our best scientists. They go on to explain that a group of timid, stubborn amphipods live in a nearby burrow. 4 types of amphipods live there: amber, bronze, copper, and desert. They live in a burrow that consists of a hallway and 4 side rooms. The side rooms are initially full of amphipods, and the hallway is initially empty. They give you a diagram of the situation. The amphipods would like a method to organize every amphipod into side rooms, so that each side room contains one type of amphipod, and the types are sorted A to D going left to right. Oh, okay. This is actually more of a shortest path search. Okay. Alright, so amphipods can move up, down, left, or right as long as they are moving into an unoccupied open space. Each type of amphipod requires a different amount of energy to move one step. Amber amphipods require 1 energy to move, bronze 10, copper 100, and desert 1000. Okay, fine. You want to use the least total energy to get all the amphipods into their positions. Okay. However, because they're timid and stubborn, the amphipods have some extra rules. Oh man, okay. Amphipods will never stop on the space immediately outside any room. They can move into that space so long as they immediately continue moving. Okay. Amphipods will never move from the hallway into a room unless that room is their destination room. And that room contains no amphipods which do not also have that room as their destination. It can stay in that room until it leaves the room. Okay, so it can go out, but it can't come back. It has to go to its destination. Once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. That is, once any amphipod starts moving, any other amphipods currently in the hallway are locked in place and will not move again until they can fully move into a room. Okay. I mean, in some ways these restrictions make it easier, because they're reducing the amount of branching. Alright, so if I understand this correctly, when an amphipod comes out of a room, it has to go somewhere in the hallway. And once it gets to that place, it's stuck there until there's a clear path to move to the correct room in one big sweep. Now that's interesting. Okay. So in this example, that one moves into the hallway and it moves there. Then you take the C and it goes to its destination. So you could argue that first goes to the hallway and then goes to its destination. Like those are 2 steps. A desert amphipod moves out of the way. Taking 3 steps and using 3,000 energy. Okay. Interesting. I mean, we could probably solve this by hand. Like, you could move A here and then B. You could move A out, then you could move C out here, and then you could move A back in, and then this A goes in. Try and solve it by hand just for fun, and then actually write the code and see. So if I try solving it by hand, what do we get? So we need to look at scores. D is an expensive one to move, so it's like 1, 10, 100, 1,000. Okay. So it's like, I don't know, move A to here. So like put A here. That cost us 2. Then move C here. 1, 2, 3. So 300. Then move A back down. 1, 2, 3. And then move this A here. 1, 2, 3, 4, 5, 6. Then what? D has to be, we have to minimize the amount we move D. So if we moved C here, one, two, three. Okay, let's say we move C here. That's 200. Then move B here. That's 1, 2, 3, 4, 5, 6, 7. 70. Then we can move the Ds. So that's 1, 2, 3, 4, 5, 6, 7,000. And then another 7,000. Looks like that. And then B. 1, 2, 3, 4, 5, 6. 60. And then B. 2, so that's 20. And finally C. 1, 2, 3, 4, 5, so that's 500. And C. 1, 2, 3, 4, 5, 6. 600. So that. Is that the solution? Yeah, well, if it's right, then at least we'll get part 2 enabled. But obviously we're going to have to code something. We need to sum these numbers, sum calculator. 15761. No, it's too high. Interesting. Well, I mean, we should probably solve this stuff with code. Although, what did I do wrong? I think that first moving C around is also expensive, so we should like it would be better if we move these. Okay, let's try this again. It's actually quite fun solving it analytically. So I think we want to clear the path for C's first. Now there's a C here that wants to move, and there's a C here that wants to move. So we have to move these things out the way. So we can move like A here. That's 2. Say move it here. Hello, DJ. Trying to solve part 1 by hand. But if I can't, then we'll solve it with code. Move A there. It's basically like a puzzle, like those puzzles where you gotta move blocks around, but they can't go through each other. Move this A here. 1, 2, 3, 4, 5, 6. 6. But you gotta do it with the minimum energy spent, essentially. But D costs 10 times more than C, which costs 10 times more than B, which costs 10 times more than A. So you kind of want to move D and C around like minimal number of steps, and you can afford to move A's and B's around more often, sort of. So if I move A's over there, then that's an issue. Okay, fine. I'm gonna move B. So it doesn't really matter. We can move B here, I suppose. 1, 2, 3, 4, 5. So that's 50. Now we can move the C's in. So 1, 2, 3. 1, 2, 3, 4, 5. So that C goes there for 500. And this C, 1, 2, 3, 4, 5, 6, 7. That C moves there for 700. I might as well move the A's right now. So 1, 2, 3, 5, 6. Okay. Far so good. But the D's are the expensive ones. So we have to move this B. 1, 2, 3, 4, 5, 6, 7. So move it to there. That's 70. Now the D's. 1, 2, 3, 4, 5, 6, 7. So that's 7,000. And the other one's 7,000. And they both end up there. And then 1, 2, 3. So that's 30. And finally 1, 2, 3, 4, 5, 6. 60. Is that better than what I did before? It is. Let's see if that's the right answer. No, it's still too high. There's a better way? We're gonna have to use code. Yeah. I guess we're gonna have to use code. Unless we try one more time. I mean, this is actually fun. The key seems to be... I think we moved B a bit too far. Let's try this. So we move A, let's say here, for 2. And then... I don't know. Or 3. This is gonna just end up being the same, isn't it? Well, we'll try it. Then we move this A over here. So that's 2. Okay, that looks good so far. And this we move to here. 1, 2, 3, 4, 5, 6, 7. So that's 70. So we're keeping things tight. 1, 2, 3, 4, 5, 6, 7, 8. C slots into place for 800. So we see that's minimal for C. And A can go in there. 1, 2, 1, 2, 3, 4, 5, 6, 7. Oh yeah, C can move. 1, 2, 3, 4. So that's 400. Now it's Slightly tricky. Well, okay. 1, 2, 3, 4, 5, 6, 7. Move the B here. So that was 70. And then the D's move. So 1, 2, 3, 4, 5, 6, 7. So it's 7,000, 7,000. That's like absolutely set in stone. That would be spending 7,000 plus 7,000 to move the D's. And then the B's. 1, 2, 3, 4, 5, 6, 7. So it's basically 70. And the A. 1, 2, 3. Another 3. Is that better? What did I have before? So before I had 15425. That's 15425. It's the same. Alright, I think we'll have to use code. Actually solve this with code. Hello, Maro. It might be an easy one. I don't know. It looks like a Dijkstra shortest path type thing. I was trying to solve it by hand, but apparently I didn't get the right answer. It's like those puzzles where you move blocks around, but they can't go through each other, so you got to get them to their correct place. It'll take a while to code though, because we have to. There's a lot of stipulations. Okay. So how are we gonna? Alright, so how do we define a state? I just I guess the coordinates of where A's and B's and C's and D's are. So but alright. Let's try and process this. We don't need to store it as a grid, we just need to note the coordinates. Alright, so for each line, we're gonna have to say So we just want to know where the A's are, the B's, the C's, and the D's. So it's just like 8 coordinates, that's it. A locks, let's call it. B locks. Hello, Lindblom. C locks. We are solving a puzzle, sort of. It's like those. What was the name of it? There was a commercial board game which was made where you it was something to do with like traffic. You had like rectangles representing traffic, like cars and stuff, and you had to move them around on the board to get cars from one place to another, but they can't go through each other. But then there's a lot of puzzles based on that type of thing, but I think it was, at some point, it was a commercial board game as well. That's basically this. We're given a diagram of where the A's and B's and C's and D's are, but we have to move them into their correct slots, which is A's, B's, C's, and D's. So we have the initial positions. And then for each line, we'll say J in enumerate line if, well, this is a chance for me to try the new, I say new, it's been around for years, the Python switch case. Python switch statement that I've like never used. So it's like this, apparently. Okay, so just append the location. So here it's case B. B locks append case C. Case D. Okay. So we should have let's define a state. Yeah, just define it like this. I mean, would need to be an ordered, an unordered. Yeah, because if A is here and A is here, that's the same as the first A being here and this A being here. So these have to be sorted so that it has a unique order. So we should say you can feed it in lists, but we'll actually do this. So we'll sort the list so that it's always in one order, so that we can say two are equal if two states are equal if the A's and the B's are in the same state, but it doesn't matter if you swap A with the other A, it's the same state. Okay. Do we need hash? I don't know if we're even going to hash it. We definitely need equality. It's going to be like this. Doesn't like us doing that. Can we just yeah, okay. And I love it being 30C at 4 AM. Oh, goodness. Okay, so that's a state. What we need? Probably need to hash it. Yeah, we need to hash it. Define hash return hash. I guess it would just be that. What else do we need? C with 80% humidity. It's pretty hot. That was basically how it was all year when I lived in Saudi Arabia for a while, but like we never really went outside. Everywhere inside was very air conditioned. Now what? So we've got a state. We can say initial state equals state with that. Okay. Let's try printing that then. Oh, we'll need a Is it not rep? Or we do this one. String return Oh, yeah, well, okay, fine. Just cast string on that. Cast... Oh, okay. You have to cast string on the... do string on the tuple. There we go. Alright, so that's... 1133, 114... It's too many. What? A, B, oh. That's because I messed with this. I messed around with it. Now we shouldn't change it anymore. Okay. Alright. So that's what a state looks like. And it's actually quite compact. There's not even many possibilities for it. Like, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. But you're never allowed to place things here above these things. So it'd be like, take away down to 18, 17, 16, 15. So there's 15 possibilities for each of these. So it's less than 15 times 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 15. Okay, that's quite a big number, but still, many of those are not even possible states because you can't even get them into that position. So, I mean, it doesn't matter because we're not going to iterate over all possibilities. But that gives an idea, roughly, for what the worst case branching we could get is. And then what? Alright, so that's the initial state. Now we have to work out so we have to just we have to write down some coordinates that like special areas. So the A I don't know, A slots equals, and then it'll be so that's 1 1 2, so it'll be so like 2 3 and 3 3. 2 3 3 3, right? So yeah, 2 3 3 3. All right. And then we've got the B slots. It would just be one space, 2 spaces to the right. So these become 5s. These become 7s. I wonder what part 2 is going to be. It's become 9s. All right, so that's those things. And then the other thing is the corridor spaces. We're allowed to go into the corridor, but we're not allowed to go to these 4 spaces. So basically we start from 1 1. So it's 1 1. And then we've got 2 2. And then 4 4. No. 1 1. 1 2. 1, 4. Like the row is always, so it's 1, 1, 1, 2, 1, 4, 1, 6, 1, 8. Eight. 1, 2, 4, 6, 8, and then 10 and 11. Okay, so that's the corridor. And that's it. We've encoded this entire thing because there's not actually much. Everything else is fixed, and it doesn't matter. You never actually go off to the sides or anything. Okay, so there are basically two types of movement. One is where you start, one of these starts in one of those slots, goes out into the corridor, and goes left or right, and then ends on some corridor space. That is one type of movement. The other type of movement is the reverse, where you start in a corridor, but you're only allowed to go to your correct slot. So if C is sitting here, then he's allowed to do a down movement. If either both of these are empty, or that one's empty and that one's got C. So yeah, that are very few possibilities for movement. Then that's a important point. So okay, so basically we want fine. So given a state, we want to get a new state, which is basically all. We want to get all possible neighbors of this state. Um, that means we go through all the possible moves that can take one of these out, and then we go all through possible moves that can take them in. um, fine. How do we do this? So we want to say do I really want to do it like this, or do we want to say um Okay, fine. So we do for, let's say, car in ABCD. The locks is going to be, how do we do this? Okay, just say a maps to self.alocks. I mean, if we'd done, yeah, this is fine. And then just do b maps to b locks. I mean, alternatively, we could, ooh, what if we make it a dictionary? Yeah, we could do that. Just say, and then we do this is going to be like this. Self.locks a equals that. Okay. Okay, so that's the why is it complaining? Okay, fine, do that. It wants me to do it that way. Then oh, now this needs to be changed. Okay, well, do the values, I'm gonna check this. So in Python 3.7 onwards, it maintains the insertion order, which is nice. So now we can say this. We just say tuple of self.logs.values, because it should come out in the same order that we put them in. So it's going to be that, and then you just have to do well, we don't want to do that. We want to say that. Okay, let me just test this out. Okay. Okay, that looks good. Alright. Now. So, okay, we don't need that anymore. So we now say, yeah, for Carol. Right. For log in self.log locks. So now we iterate over the two locations of these things, and then we say there's two possibilities. If it's in this region, i.e., okay, so if lock 0, the row, is greater than 1, that means it's in these buckets, then I just want to note that up move, and we take it up and go somewhere. Else, if it is exactly 1, then the only possibility is a down move. Okay, so far so good. I need some coffee. So, in an up move, okay. So in an up move, we want to see if we're already in the correct place, and either we're at the bottom or we're the second row up, but below us is the correct. How do we express this correctly? If So if we're in the wrong bucket, then we're automatically eligible to do an up move. If we're in the right bucket, we may still be eligible. It depends whether there's something below us. So if lock, so many little variables I need here. So home column 1, 3. They should be curly. So that's the home column. So if block 1 equals home column car. So if we're in the right car, okay, and if we're at the bottom, which would mean 1, 2, 3, or we're one row up, and there isn't another one, correct one below us. So what we're trying to say here, and the position below us, which is block, so it'll be 3 block 1 is in self.locks car. That means, so if we are on the bottom, so here, or we're here and there's a, and so we're either A is here, or A is here and there's an A below us. In both of those situations, we're not allowed to leave. Like we're home. We're done. Let's continue. So if we're not in that situation, then either we're in the correct bucket, but there's something below us, wrong below us, or we're in the wrong bucket. In both of those situations, we're allowed to move. Okay. And now for So to check for clear path, basically we want to check all possible corridor spaces. Corridors. I don't think we even need these variables here. Move these static variables. Alright, so okay, for corridor space in corridor. We want to see if there's a path going up, so we need to say so path equals that. I'm gonna have to make another variable here. Let's say or we just want a how do we do this? Yeah, just do it like this. Isn't there a reduce union sort of thing? We'll just do it like this. That's all locks. Because I just want to know them, because we'll need them here. Okay. For row in range say from oh god, starting from the next space up. Lock 0 -1 and ending on row 2. Going backwards. So we start the next space up finish in 2. So really all this does is just add this space to the path if we're on the bottom row. And if not, then we don't do anything. Okay, so that's just that. Maybe it's better if we just do an if statement here. If lock 0 is 1, 2, 3. Then path dot append. So the first space we'd have to go to is 2 and lock 1. Wait, this isn't right. Is it? Yeah. This should not be indented, so we're not... So if it's in its correct column, and if this thing is true, which is saying if it's at the bottom or there's that thing above it, then we skip that one. So basically in every other situation we do this. Okay, yeah, that's fine. Corridor, space, and corridor. We do. And then we should really be doing like a flood fill type thing, but it seems pointless. Alright, so we then bring it into the corridor. And now we just say if, okay, the delta is going to be -1 if corridor space 1 is strictly less than 1, else 1. So if -1 if we're going left, 1 if we're going right. Then we do for j in range. So starting from lock 1, and ending on corridor space 1 plus delta. So the very last thing we visit is the corridor space we're trying to get to. I'm adding delta each time. You put that on the path. This is just a really possibly overcomplicated way of drawing the path that goes up and to the right, or up and to the left. And what do we add here? Path to append. It's going to be 1 J. In fact, we don't need this one anymore. So that's the path. So we know where it is, we know where it wants to get to. We want to look at all the spaces, except for the starting space. We'll look at all the spaces on that path, including the destination tile. And we want them to all be empty. So if all say if any P is in all locks for P in path. So if any of those cells is occupied, that means you can't do this movement. We have to skip it, move on to another corridor space. So it may be repeating work, but that's fine. So if we get this far, that's actually a viable space to go to. So the cost is going to be length of path times this is going to be move cost. It's going to be like this: 1, 10, 100, 1,000. I'm pretty sure I could have solved part 1 by hand by now. It's going to be move cost R. We want to yield the neighbor. So the neighbor How are we doing this? I guess we have to redo. Okay, we have to make a copy of this. Basically, we have to make copies of these. How do we do this? Just say new locks equals we'll be able to just make a clean copy. But we change take what it was before, turn it to a list, remove the location of where this place was, which is lock. And then we add where we want to go now. Is corridor space. Oh, damn it. The cost is not that. It's well, we haven't worked out the cost yet. Path cost is going to be the Hamming distance. Is going to be so what are we comparing? We're comparing corridor space with lock. Absolute value of lock 0 minus corridor space 0 plus absolute value of lock 1 minus corridor space 1 times the base cost. The path cost, new car locks, finally we yield a new state given now we have to replace new locks car with this modified new car locks, and finally we have to do this. We have to say new locks A, new locks B. I'm sure there's a cleaner way if we could have done all this, but we'll stick with this format now. Didn't like this. And that's the state, and we also have to yield the cost. Yeah, that took longer than I expected, and that's just for an up movement. We have to do the same for down movement. I could have made a method. Oh, we can still do that. Let's separate this out into a method. So we'll say fine get path length you see why I solved this by hand in the end. Seemed easier. Yeah, I tried to at the start of the stream. I think I didn't figure it out, but I didn't spend that long on it. Decided I don't know what part 2 is going to throw at us, but I do agree. I think if I had just carried on, I probably would have solved it by now. I think I'm close though, although I don't know if any of this is going to work. Path length from probably could have been generalized more and just not have so many rules in it and then still run in time, but so get path length So from a given position to a given destination, we want to find the path from start to destination, surely. But what's the problem? Well, I guess it's different. If we start in the bucket, we have to go up first, then go to the side. If we start on the corridor, we have to go to the side, then go down. So we just say let me turn the AC on. Okay, we'll just do the two cases separately. If start 0 is greater than 1, that means we're in a bucket. No virtual paper. We're in a bucket, that means we start, go up, then left, right. Okay, and then we just have to copy this logic from down here. So alright, so if start, I was doing Advent of Code 2024 yesterday, got done with day 2, but man, I struggled. Day 2, let me have a look at day 2. Day 2. Part 2 of day 2. Let's see if I remember. All increasing or all decreasing. Any two adjacent levels differ by at least 1 or at most 3. Let's see. So part 2. Okay, so that I think, yeah, that doesn't seem too bad. I don't really remember it that well, but part 2. Oh, I see. So you got to remove a single level. So I guess you just try removing each thing one by one and seeing if the remaining array is fits part one. Oh right. Yeah, I guess that's the insight. Once you realize that, I mean, I guess that's they sort of hinted at it with that sentence, but yeah, I can see why people might try to do it without removing it. So just like kind of count like how many bad levels there or something. I don't know, but yeah, I don't think it was too bad when I did it. Where are we? You don't need to remove it. I added a retry and skips the unhealthy value. Yeah, I think that's probably what I did. In fact, I probably have it right here. Wait, what's decode.py? Why do I have that? Oh, that's not append of code. That's something else. Why did I put it in append of code? Right, 2. Yeah, this is my 2. So basically I do a Python slicing where I take what the report would look like if I cut out the ith thing, and I just piggyback off the previously defined isSafe method, which was used for part 1. But yeah, Python's quite nice like that. Slices, generators, summing booleans. I mean, you wouldn't even need this. You could say sum of change what I've selected here to sum of that, or what I've test. No, I did get muted. I knocked my microphone. I'm gonna have to make a proper stand for my microphone. Right now I'm using a What even is this? It was a carton that previously held hot and spicy seasoning powder, which I hollowed out and then stuck the microphone in it, and then I carved a little hole and put the wire through the back of it, and that's just kind of holding it up. But every time I stick it in my suitcase, like, it all gets squashed up, so now it's just a really bent... Well, I've got to show it on camera now, don't I? That is what I've put my microphone in. Just to keep it upright and shield some sound as well, but... Yeah. It's almost... I'm gonna have to buy another packet of hot and spicy seasoning powder and use it up just so I can make another microphone shield. Okay. What am I returning here? Length of the path, isn't it? Okay, so that is big method. We can probably cut out most of this logic now. So we say viable to leave, check for clear parts. So we don't do any of this. Well, we do, but we just say path length equals get path length from location to the corridor space, and path cost equals basically that. Wait, why am I... Why? No, we don't want path length. We don't care about path length. It's a true-false thing. Is path clear, let's say. We can move from start to desk without interference, without an obstacle. Return false here. Return true here. Return false here. Return true here. And down here... It's so much messier than I thought it was going to be. I guess because it's just very fixed. If they just made it a more general problem, then it would, in theory, it would be a harder problem. Fewer restrictions. But just easier to code. So you'll have to go anywhere and do anything. So if self dot is path clear from the location to the yeah, the corridor space. So if there's a clear, or we'll say if there isn't, Then we skip this one. Alright, so path cost equals would be the movement cost times by the absolute value. Yeah. I could make a absolute value thingy, but new locks equals self.locks copy, and then we do all this. There's no quick way of doing this, really. And then new locks equals that. Why doesn't it like that? Probably will be fine when we run it. And yield state and the path cost. Okay. That's an up move. One up move. But that's like most of the algorithm. Oh, and the down move as well with most of the algorithm. Then it's just a case of... This is literally just the get neighbors function. We still have to write the actual breadth first search. Not breadth first search. It's going to be Dijkstra. It's okay, we know how to code Dijkstra. Normally the Dijkstra bit is the longer bit, and get neighbors is just like a up, down, left, right, whatever. Right. So this is a get up, go up move. Okay, down move. What do we do? So if we to see if there's a down move, we're gonna look for the correct bucket for this home column, we called it. So we need to look at what's in the home bucket. If it's completely empty, okay, so the top space of the bucket has to be empty. If it isn't, we literally can't move into the bucket. So if we have to have this. If so, it's going to be 2 home column R. In all locks, then we can't go there. Continue. We can't. It's blocked. But if it's empty, then we can say if three not in all locks, then destination is going to be that. That's our destination. It's empty, so we can go there. Elif is in self.logs car. That means my mate, if I'm A, then my other A is already home. Then destination is 2. We just go on top of him. Okay. Else, if it's neither of those, then it's not viable. So we continue. Okay, this is okay. So we have a destination. So just do the same logic as above. Essentially, if, yeah, basically all this. Okay. If not, self.path is path clear from lock, which is where we are, to dest. Continue. So there is a clear path. Path cost equals that times absolute value of lock minus dest times dest. Let me do this thing. Space, but this time it's dest. And new locks yield state new locks A new locks. Yeah, okay. And the path cost. Okay. Bit of a mess, but I think that is correct. We're yielding the distance, the state and the distance. Right. See if that actually compiles. Okay, so far so good. We didn't use that. Alright. To define Dijkstra. Goal. What was this question again? They want us to give the least energy. Okay. Right, so we do standard stuff and can't remember. From heap queue import thingy. Don't remember what it's called. Dijkstra should have a K in it. Oh, should it? Did I not? Dijkstra. Can't remember my cues. Well, there's also this one. Right, whatever, just use that. We're trying to find distances. That's going to have to be a dictionary. And then we need a cue. Put the distance followed by that. We can say start. It's distance 0, so we do dist. Start like that. While not q.empty, the current equals q dot get. Probably on lazy deletion or something. If d is greater than dist current, that means we've found that this is lazily deleted. We don't care about this, so just continue. If current equals goal, at this point, that means we're done. This is the yeah. Return dist goal. None of this is tested. It's not going to work first time, is it? And if it doesn't work first time, I don't think I even have much time left. Okay, so that's that. Then we do the neighbors. This is probably the longest get neighbors function I've written in a long time. Sure, there must be a much cleaner way of writing it. We could have just done generic Dijkstra moving things space by space, reading the map with the obstacles and everything. It might have just worked. All right. Well, there are. Well, they do have the rule that you're not allowed to stop over a bucket. That is that wouldn't generalize exactly. Anyway, for neighbor in okay, so we're returning neighbors and distances. Okay, so it's gonna be neighbor edge cost in, so it's current dot, the current is a state. This is hashable, right? Yeah, we made it hashable. Current dot get neighbors. What would it look like? State dot get neighbors. Okay, so neighbor dist equals d plus cost. If neighbor not in this, so we've never seen this before. Or we have seen it before, but we've now found something better. Strictly less than this neighbor. Then we have a new best path to neighbor. And we want to pop it on the queue. It. And that's Dijkstra, and then start from the initial state and goal. It's gonna be, well, it's gonna be, you have to write it explicitly. We have to say goal equals state. It's going to be it's going to 2 3 3 3. I did write this down already and I deleted it. Of course I did. It's fine. 2 3 3 3. So that's the, no. That is the ALOX. And we've got 2 5 3 5. We just 2 7 7 9 9. That's the goal. Finally, print Dijkstra start goal. Start initial state. Alright, that's a whole bunch of stuff untested, as always. I do not trust any of this. How did it end up so... When I first started writing this, I didn't think it would end up like this. It looked conceptually pretty clear what's going on. Oh well. Oh damn it, we need a... I hate doing this. Because it's not... Okay, we need a less than or equal to. Like, you shouldn't really do this. You should, like... If you don't think states should be less than or equal to each other, then you shouldn't really make a less than or equal to method, but it's just a hack. Everything is less than everything else, sure, why not? Oh, it's less than or equal to? No, less than LT, less than, yeah. And, oh, it finished. Hex's room, oh god, wow, it went dark all of a sudden. The sun just dropped. 15385. Oh my god, if this actually works. Whoa! Okay. It worked. Like, out of all the programs that could have worked first try. I was really not expecting this one to work first try. Let's hope for a nice part 2. As you prepare to give the amphipods your solution, you notice that the diagram they handed you was actually folded up. As you unfold it, you discover an extra part of the diagram. Between the first and second lines of text that contain amphipod starting positions, insert the following lines. Oh no. Oh, we've not generalized for this. We're gonna have to... Wait, let me read on, see what it should... it's gonna be a... Okay. It might not be too bad, actually. Yeah, there's like a couple of places we have to write a little bit of a hack, but it's actually not terrible. I don't really feel like doing it today, though. Yeah, it's actually not too bad a change, but we just need to adjust for a variable number of things in one column. For all I know, this might only take me like 10 minutes or something to change. Still, I don't feel like doing it today. As we get closer and closer to 25, I'm becoming less and less keen to do like 5 or 6 days in one day. In the first couple of days, I did like 5-hour sessions. Alright. Well, that's slowly getting closer and closer. Marathon the rest. It's alright because I set my YouTube videos of each of these to release once per day, and the releases are only up to like day 12 or something. So in theory, I've got like more than a week. You know, like I can be slow by a whole week, and the YouTube videos will still be released one per day. That's because I did so many in the first few days. I may have spotted a possible bug in my code based around my misunderstanding of record structs and record classes when they first appeared. It might not be an issue if I can bother to go back and check. Okay. Alright, it was a nice problem, actually. I think coding part 2 will actually, in some ways, make my code cleaner, just because you actually have to generalize it a bit more to a variable number of things in one column. That actually probably makes some bits actually not quite as specific. So yeah. It took a few seconds to run, so this next one's probably going to take a long time. And this can be improved to A star. You never know with A star. Like, does it make sense in this context? To some extent, maybe. Like, when you take things out of their bucket, you don't want to put them far away from where they're supposed to be. So A star would try and avoid that. I guess it would help, yeah. A star's probably faster. I'm not going to bother, but probably would help. Like, you don't want to, if you can help it, you don't want to move B all the way there and then move it back. But sometimes you do need to do that, because it's the only way. But still, if you've got the choice, you don't really want to move it that far. So I guess A star is probably actually good for this type of problem. Plus, it takes into account the higher costs of D and C. A star will actually account for that and be more careful about moving D's and C's about. In fact, now that I think about it, A star might actually be very strong on this. I mean, it's always an easy change to make. You just add in a heuristic, so yeah, I might actually do that. because A-Star is also going to, as soon as it sees a chance to move something into its correct place, it will take it as soon as possible, because that immediately frees up the distance between you and the goal state. You're immediately cutting away a huge heuristic distance. So A-Star will prioritize doing those, which is exactly what you want. Like, if you can move into your desired position, you absolutely should do it. There's no reason not to. Yeah. And right now our code doesn't necessarily do that. It might try moving up before moving down or whatever. We don't necessarily prioritize, but we should always prioritize moving down. That's a final move, and there's no reason not to take it when you can. So yeah, I think A-Star might actually be good for this. So there's two things we can try next time. We can try actually solving the problem and throwing A-Star in. See what happens. Okay. People didn't find it too bad, but I mean, it can be solved by hand. Although part 2, I don't know. Did you solve part 2 by hand, Smab UK? Or was it just part 1? Let me have a look at this. Is that actually solvable by hand? Probably. Yeah, it's a bit like a puzzle. I think you can reason out a solution. It might be hard to actually be convinced that it's the shortest, but part 2 as well. You did. Oh, okay. I guess I've done the bulk of the work now, so it won't take too long to adjust for part 2. Alright. And then it looks like day 24 is a reasonably easy part 2, given that practically everyone did part 2, if they did part 1. You can take a sneak peek. Oh, it's in code. Interesting. So apparently it has a very easy part 2. Oh, we shouldn't be doing a sneak peek if we haven't done part 2 of 23. That was a bit naughty. Alright. That's it for today. Tomorrow, do part 2, and if I have time, move on to day 24, Christmas Eve. Alright. That's it. Thanks for watching. See you next time.